Hello guys, in this video I will explain you stereographic projection. Stereographic projection is used in structural geology to analyze two-dimensional structures on two-dimensional plane. So two-dimensional plane is in this case this paper, and three-dimensional structure is a bedding plane, fault plane, a silicon line, any measurable planar or linear structure formed during geologic processes. So stereographic projection is a lower hemisphere spherical projection which allows us to show subsurface configuration of different structures. So because structures will be aligned in different directions and they may also have different dip angle or plunge angle. So we want to show this internal angular distribution or structural architecture at the subsurface or surface. So in order to do that, we collect measurements, strike and dip measurements for planes, trend and plunge measurements for lines. And with these measurements, we can plot planar and linear structures on a two-dimensional projection area, which is called stereonet. So this stereonet is if you cut Earth along equator and put a grid system with 10 degrees and 2-degree intervals, this is how it will look like. So with this grid system, now we can use these intervals and plot different angles in different directions. So basically, the components of StairNet, first of all, we mark these directions on StairNet, north, south, east, west, or you can also mark azimuth 0, 0, 0, 0, 90, 180, 270. So whichever convention you want to use, you can mark according to that. But in any case, you have to mark all four directions to make sure when you rotate tracing paper in different directions, when you come back to north, you want to make sure your tracing paper is in place. And other than this, we have these lines and grid network. So basically, these horizontal lines looks like latitude. These are small circles, and vertical lines, these are look like they are looking like longitudes. So these are great circles. And there are, let's take this piece of paper. So there are thick lines in between two thick great circles. We have 10 degrees. And between two thick great circles, we have finer lines. And these fine lines are basically 2-degree intervals. With these 10-degree and 2-degree intervals, we can basically plot any dip angle between 0 and 90 degrees. So first, I want to show this example. Here we have this ball, which will represent our spherical projection area, like this stereonet. And if this is the stereonet or lower hemisphere of the Earth, there are so many different structures with different dip angle and different strike orientation. So this paper will represent one of those layers. Let's say this is a bedding plane. So this bedding plane can be oriented in this direction, for example. If this is the case, now when you look at this bedding plane from top, all you see is this straight line, which is the strike of this bedding plane. And if you remember what is strike is, so strike is basically a watermark. If you fill this, if you fill this ball with water, that horizontal watermark will be strike of the layer, or it is the orientation of this layer, bearing of this horizontal line with respect to north. So when we hold this layer perpendicular, in this orientation, dip angle is 90 degrees. That's the angle between this plane and horizontal plane. Because now this desk is horizontal, we can measure angle between this desk and this plane. It is 90 degrees. So do we have a vertical plane? So this vertical plane will make just a straight line going through the projection area, and it will be just not curved like these other great circles. and it can be oriented anywhere between 0, 0, 0 to 360 degrees. So if we have a vertical plane striking, let's say north 45 east, this is how it will look like. It will be a straight line in north 45 east direction. Or if it has an attitude of 0, 90, 90, which means striking at 0, 90, which is right here. Here we have 0, 0, 0, and this is 0, 90. So this is the strike orientation. Because the second component, which is dip, is also 90 degrees. So I'll hold it just vertical. So this is now a vertical plane in east-west direction. So anywhere, any strike orientation can represent basically a vertical plane. So what about this plane is if this plane is dipping in one direction? So in this case, if it's a bedding plane like this, dipping this way, dip direction is if we pour some water, whichever direction it flows, that's the dip direction. So if we pour some water, it will flow in this direction. That means this layer is dipping this way. So if I, so since um, these layers, if you first let's find the horizontal line on this plane because that will mark strike orientation. So if you find a horizontal line which will be parallel to this line, it will be basically in the same direction with north-south reference line. So we have now a north-south striking layer and it is dipping this way to the west. Let's see how this layer will look like on this spherical projection. If I trace if I trace the intersection of this plane with this ball, that will basically mark its expression on the spherical projection. So I will do that. Right here we have this, then this, then this. So this red line is now outline the intersection of ball with the plane. I will just move this plane and let's see how it looks like. So now look at this line. So it is a great circle. It is curved. It is not a straight line. It is actually curved like these great circles. So because of that, planes will make great circles on this, staring it. So each one of these great circles on the projection actually represents a bedding plane. Now all of these great circles are connecting to north-south. So all of these lines are north-south striking planes with different dip angles. So right here we have a vertical plane striking north-south and dipping at 90 degrees. Because of that, it is a straight line. This curved line, which is another great circle, is at 80-degree dip angle. Here we have 90-degree dip angle. Next one will be 80 degrees, and this way it will decrease. So right here on the perimeter circle, it will be 0-degree dip angle. So why this is the case, let me show you. So we are looking for the intersection of the ball with the plane. So if I put this plane over this ball like this, you can see the intersection between plane and ball is the outer circle, outer circle of this ball. So that's basically representing this horizontal plane. So that's why if we outline the outer circle of StareNet, that means there's a horizontal plane among our measurements. So these are planes. What about lines? If we have a linear feature, it can be a fault silicon line or a mineral stretching lineation, different type of linear features, something like this. So if we have a line, let's say if we have a vertical line, so vertical line, which means it will the plunge of this line will be 90 degrees. So the angle between this pencil and this desk is now 90 degrees right here. Okay, so in this case, if I hold this pen vertical like this pen will make a single point right at the center of projection. If I tilt this pen at an angle, now it is plunging in this direction, or this direction. So as you can see, plunging lines will always plot in within one of these four quadrants. Only vertical lines will just plot at the center of projection. And if there is even a few degree of plunge, it will plot in one of these four quadrants. And another thing is, whichever direction is plunge direction, this pencil will make a mark within that quadrant. So right now, if I hold this pencil like this, as you can see, it is plunging this way, plunging down in this direction, which is northwest. And where this pencil touched the surface of ball or spherical projection, it is also northwest quadrant. So this pencil will make a point in northwest quadrant, which is also plunge direction of the linear feature. If it's plunging opposite direction, then it will make a point in southeast quadrant. When we record measurement of linear features in azimuth convention, that's why we always record strike orientation in down plunge direction. So if this line, for example, this line can have a strike orientation at this point or at this point. So which one? Because it's plunging this way, in this case we record 3-digit trend from this end of the line, not the other way. If it's plunging opposite direction to southeast quadrant, then we record its trend as this 3-digit number. So in this case, let's make up numbers. If it's tilted like this, plunging like this, then let's say this is there's 45 degrees to 360. So in this case, this point will be um, um, 315, right? So here we are at 315 degrees. If this pencil is plunging in this direction, its trend will be 315. Although it is same direction, just 180 degrees from this point, still same alignment. In this kind of plunge direction, we will read trend of this pencil from this end, which will be 100 minus 45. Okay, or 9 plus 145. So that way, 3-digit number will give you some idea about plunge direction of linear feature, like we apply right-hand rule in planes. So after that, now I can show you how to plot planes and lines on stereographic projection. So this is the StareNet we use. First, mark directions on your StareNet and mark the center point. After you stick a thumbtack through the center of the StareNet, I also recommend using a tape and cover this center with tape. That way, uh, this hole will not get loose and it will not give you too much error. In the next step, we will use a tracing paper. So on this tracing paper, I already have a measurement which is plotted as a great circle. So now I will show how to plot this measurement with as a great circle again. First, this is a measurement recorded in azimuth. Normally, we don't have to know the direction. These two numbers are enough since it is recorded obeying right-hand rule. So 128 is the strike. Strike is always recorded as 3-digit number and it comes first for planes. And 50 is dip component, which is dip angle. So with using right-hand rule, we can figure out what's the dip direction. So to do that, before that, first let's find this strike orientation. So we will find 128 degrees around this primitive circle. So we always use primitive circle to plot strike for beds or planes and trend for linear features. So these three-digit numbers will be plotted here around this perimeter circle. And we use equator, north, south, east, west lines to count dip angle and plunge. So we have two-digit numbers here and three-digit numbers around the stairnet. Now let's find 128. We start from north. This is always our start point. So we start from north or 0, 0, 0 and count clockwise in this direction. And right here we are at 0, 90 degrees. And after this, you count these thick lines. These thick lines are 10-degree intervals. And between these thick lines, we have small 2-degree intervals. These, let's take this out. The other thing is this longitude, kind of looking like longitude. These are great circles, and these horizontal lines look like latitudes. These are small circles. So in any direction, thick lines, between two thick lines, that will be 10 degrees, and between two fine lines, that will be 2 degrees. So using that information, now we can count these thick lines after 090. Here we are at 100, 110, 120. Now I will count small circles with 2-degree interval. So 122, 124, 6, 8. Then you mark this point on the primitive circle as 128. This is the strike azimuth point we marked on primitive circle. In the next step, we will rotate our tracing paper and align this strike azimuth with north-south direction in order to find this dip angle of 50 degrees. Before that, like I said, if we don't know dip direction, first we apply right-hand rule and figure out dip direction. To do that, it's a simple way. You find strike azimuth point and put your thumb on that point and align your thumb with this strike orientation. If you open your hand, these four fingers will show the direction. In this case, this layer should be dipping southwest. So we found southwest dip direction. That means we have a westward dipping plane. So you will count 50-degree dip angle from west towards center of the projection. If you have an eastward dipping plane, then you start from east and count dip angle towards center of the projection. Here we have 0-degree dip angle, and at the center we have 90 degrees. In between we have these different values of dip angle. So let's rotate tracing paper. So which way you should rotate tracing paper? That's another question we always receive. Basically, whichever direction is closer, you should rotate your tracing paper in that direction. So if you rotate 128 all the way back to north, it will be over 90-degree rotation, and you don't want to overturn this layer. You don't want to change its orientation. Because of that, we rotate 128 to south because it is closer. So rotate 128 to the south. Now we align this plane with north-south direction. And you can see these great circles with changing dip angle from 0 to 90 degrees. One of them will represent this 50-degree dip angle. So start from 0 and count along the equator, count 50 degrees because that's what we have in the measurement. Start from 0. Here we are at 10 degrees, 20 degrees, 30 degrees, 40 degrees, and 50 degrees. So that 50 degrees is the dip angle of the measurement. So there is only one single great circle corresponding to that dip angle. Now draw that great circle. This is the great circle we are looking for. If you rotate tracing paper back to north, because you will do this all the time, that's why it's important to mark directions and center. So when we rotate tracing paper back to north, now this great circle should be curved down to southwest direction, which is dip direction of the layer. So this curvature of great circle will show you dip direction of the layer. If you have a northeast dipping layer, then this great circle will be curved to the northeast direction, in that direction. Let's find another great circle. This time I will show a measurement in quadrant. So north for the east, 80 degrees to the southeast. In quadrant, we don't have to worry about right hand rule because we already have all information we need. We know dip direction, we know dip angle, and we know strike orientation because everything's recorded in quadrant convention. We just don't have to use right hand rule. Instead, we use quadrants. Strike orientation of layer is for north, 40 east. That means we have a strike orientation in northeast quadrant right here. So we are looking for a line which is the strike orientation of this plane in northeast quadrant, and it will be 40 degrees off the north in the direction of east. Start from north and count 40 degrees around primitive circle. Mark that point. That's the strike orientation like we did for azimuth. So start from north, count 40 degrees using this thick great circles, small circles. So here it's 10, 20, 30, and 40. Mark this point. So that's north, 40 east strike orientation. Like we did for first measurement, now we will rotate this point to north-south reference line. Because this time we are closer to north, we will rotate tracing paper this way and move this point to north-south reference line. And dip direction is southeast. It's dipping 80 degrees to the southeast direction. So it's an eastward dipping plane. In this case, we'll start from east and count 80 degrees from outer circle towards the center, and we'll then mark that great circle. So right here we are at 90 degrees. So if I come back just 10 degrees, that will be 80 degrees. So this is 80 degrees. So I can just draw that great circle. So this is the second measurement. Now let's rotate back. It should be curved to southeast direction. As you can see, it is slightly curved down to southeast direction. That means we did that correct. Other important thing to take a note here. This first measurement had a dip angle of 50 degrees. And look at the geometry of this great circle. It is more curved on the stereographic projection. And the second measurement has a dip angle of 80 degrees. And look at the geometry of the second line. It is now straightened up because it's getting closer to center. And at the center, it will become just a straight line. So that means steeply dipping layers will plot more less curved great circles on the stairnet, and shallow dipping planes will be more curved great circles, and they will be closer to primitive circle. As you get closer to center of projection, great circles will be straightened up, and they will become steeply dipping layers. So this is how we plot planes. Next, I will show how to plot lines.